Welcome to part 4 in the overview of pattern relationships. In part 1, we motivated the need for pattern relationships that go above and beyond traditional pattern collections. We also gave an overview of the different types of pattern relationships we're talking about in this module. Part 2 presented a case study from the domain of avionics control systems to help to motivate some of the key architecture patterns like publisher-subscriber and broker that are important for concurrent and network software. Part 3 discussed the concepts of pattern complements and pattern compounds, which paved the way for the discussion in this part, pattern sequences. In addition to describing what pattern sequences are, we'll also have a chance to motivate yet more POSA and Gang of 4 patterns. A pattern sequence generalizes the progression of patterns and the way that a design can be established by joining successor patterns with predecessor patterns by having the context of the successor pattern be driven in part by the outcome of the predecessor pattern. So in a sense, a pattern sequence captures the unfolding of a design pattern by pattern. If you take a look at the POSA 2 book, you'll see some good examples of pattern sequence patterns, or patterns that are used heavily in the pattern sequences we'll be covering. If you look at the POSA 4 book, especially chapter 6, you'll see an example of a pattern sequence that's used for communication middleware. And we'll be focusing in on the patterns in that sequence throughout the rest of this module. For this particular part, we're going to zoom in on 3 of the patterns in that sequence. And we're going to talk about how they can be applied to make certain aspects of brokers for concurrent network software more flexible and more efficient. So here's the context. When we built our middleware, when we built the implementation of the broker pattern that was based on Corba, we were very insistent on making it work for a number of different domains. We didn't want it to just work for avionics. We didn't want it to just work for telecommunications. We didn't want it to just work for medical systems, all of which we were working on with various sponsors. And by providing a framework for broker that would work in different domains, it allowed us to get a greater number of users of the software that we were developing. However, it turns out that there's no one-size-fits-all way to implement a broker. Certain mechanisms work well in some contexts, certain work well in another. And moreover, the traditional way of implementing variation in a broker tends to lead to things being ugly and messy and complicated to change. For example, if you had different synchronization code or different concurrency models or different demultiplexing approaches or different transport protocols, one way to do this would be to hard code the different alternatives as a sequence of if-else statements throughout the code. But you can imagine how complicated that is to modify and evolve over time, because you've got to change lots of different places, lots of different times. And very quickly, the structural cohesion of the design begins to evaporate in a sea of complexity. So what we did instead is we applied a classic Gang of 4 pattern called strategy in order to factor out the commonality amongst the various implementation mechanisms in our broker. Now, the strategy pattern can be used to define a family of algorithms, encapsulate each one, and make them interchangeable. In our particular case, what we were interested in was being able to interchange different mechanisms for implementing the broker. You can read about the strategy pattern, of course, in the Gang of 4 book, which I highly recommend, or you can take a look online at the Wikipedia link to learn a bit more about it. What we did is we went through our broker and systematically identified all the different mechanisms that would vary. So we had different marshalling and demarshalling strategies. We had different connection management strategies. We had different strategies for concurrency, synchronization, event and request demultiplexing, various synchronization strategies, transport strategies, you name it. If it varied, we came up with a way to turn it into a strategy. And as a result, our software became much more flexible, much more extensible, and much more tunable and parameterizable to meet the different needs of our sponsors. It turned out, however, there were some problems. One of the things that became clear once we exposed all those different strategies was that we'd moved away from having a tight coupling problem to having a potential configuration nightmare problem, because it was all too easy for either ourselves or worse, our users, to start selecting these strategies in ways that were not semantically compatible with each other. So for example, someone might say, I would like to have an event demultiplexing mechanism that uses a reactor that's not going to have any threads or locks. And at the same time, they could also select a strategy that might say, I want to have a concurrency strategy for handling requests that will be a thread pool. Well, the problem, if you're not careful, you can end up combining different strategy implementations that work fine in isolation, but when put together don't work properly. For example, if you don't have your locks selected properly and you choose a thread pool, you can end up with data structures that have race conditions and are not properly protected from concurrent access. And the more strategies you have and the more combinations you have, the more likely you are to run afoul of this configuration nightmare. So how did we solve this problem? We applied another Gang of Four pattern, this one called Abstract Factory. And we used this to be able to consolidate groups of semantically compatible strategies behind the Abstract Factory interface. Now, the Abstract Factory pattern allows you to create families of related objects without exposing subclass names. So you can have an abstract factory with a group of factory methods that create different kinds of products. In our case, it was these strategies for the broker. And then you can go ahead and you can subclass the abstract factory to make one or more concrete factories that create the right kind of products that make sense when used together. Once again, you can find more information about the abstract factory in the Gang of Four book or other resources on the web. The way we applied this particular pattern in our broker was to make different concrete factories, in other words, things that inherited from abstract factory, that were customized for different kinds of domain uses. For example, for our avionics sponsors, we grouped together certain strategies that ensured very low latency, very predictable behavior by the broker, because that's what mattered for them in the avionics control environment, control system environment. In contrast, for our electronic medical imaging sponsors or our telecommunications sponsors, they weren't quite as interested in low latency and real-time behavior. They were much more interested in high throughput and high scalability. So we created concrete factories that grouped together a set of semantically compatible strategies that optimized the middleware framework, the broker implementation framework, for those particular requirements. And that made it possible to satisfy many different users within a single code base. But there were still problems we had to deal with. As we started developing these different strategies and factories, at first we grouped them all together into the middleware. And so not surprisingly, it became bloated. It became very large. We had all these strategies and all these factories floating around all the time. And people started to complain, and they'd say, when we use your middleware, it takes up too much space. Even more interestingly, it's not always the case that you can nail down the different strategies that you want to use at design time or build time. Sometimes you have to wait until the program starts to run for it to sense something about its environment in order to select the appropriate strategies that make sense. Just as a simple example, if you bring up some software like a piece of middleware or like a broker in a multi-core environment or in an environment that has special hardware-assisted operations for transmitting data back and forth between different address spaces using direct memory access or other optimizations, it may turn out that you have different strategies or different strategy implementations that make the most sense in those contexts. And if you try to prematurely commit yourself to a particular implementation or a particular group of implementations, you're probably going to be non-optimal in some environments. So how do we solve this particular problem? Well, what we did is we applied a pattern described in the POSA 2 book called Component Configurator. And we allowed the broker and its strategies and factories to be configured very late in the design cycle, either at startup time or even at runtime. And it was able to dynamically load and configure the abstract and concrete factories and strategies when the program began to run. Now, what Component Configurator basically does is it provides a configuration or reconfiguration interface that all reconfigurable objects or components have to inherit from or somehow otherwise be associated with. And by decoupling the component interface, which has these common hook methods, from the component implementations, it's possible to be able to configure or reconfigure the state of the software system very late in the design cycle. In fact, you can even do it without having to stop, recompile, relink, and restart running applications. Now, some places that makes sense, some places it doesn't. For avionics mission computing, probably not going to be recompiling and relinking this stuff on the fly because they're safety critical systems. But there's lots of systems in enterprise computing where the ability to change on the fly, to be able to do online upgrades is very useful and very important and can be used to reduce maintenance and sustainment costs. You could also take a look at more information about this pattern either in the POSA 2 book or at this resource online. From a dynamics point of view, Component Configurator typically works by having some kind of scripting mechanism that's read by a framework that instructs the framework which services or components or objects, whatever your granularity unit is, to dynamically link in to the system, initialize, and then group together with the other services that have been brought in dynamically. And we use this particular mechanism quite extensively throughout our middleware to be able to put it on a diet. So we would only have in memory at any given point in time the particular component strategies or strategy implementations that made the most sense for the context in which we were working. And the other ones could reside on disk somewhere or be provided in some other storage. In fact, you can even go as far as to dynamically link these implementations over a network if you're willing to put some time into building the underlying mechanisms. It's worth noting, by the way, that Component Configurator is also used other places. The Java concept of an applet is a great example of a known use of Component Configurator. Likewise, the ability in modern operating systems to be able to load and unload device drivers dynamically is another good example of the Component Configurator pattern. So it's been widely applied in other places in the past. So to summarize this particular section, a pattern sequence, much like a pattern, is both a process and a thing. It represents a process composed of constituent patterns that are arranged in a particular order that captures the evolution of a system and also achieves a particular design outcome. So in the particular example we've been looking at in this part, we've seen how we were able to take a number of patterns, group them together in a particular sequence, and then use that sequence to help generate the architecture and design for our implementation of the broker pattern. So it's a nice example of how patterns are related to each other in all kinds of interesting ways. It also illustrates something else that's interesting. It shows how real-world substantial designs are often put together by composing patterns from different sources. You can see here that we have a couple of patterns from the POSA 1 book. We have layers and broker. We also have a whole pile of patterns from the POSA 2 book, things like reactor, acceptor connector, wrapper facade, and so on, which we'll talk about later in the course in more detail. We also have patterns from the Gang of 4 book, strategy, and abstract factory. So the point is that good designers have an extensive knowledge of the vocabulary of patterns, and then they know how to combine those patterns together in various related ways in order to help to be able to cover a broader part of the design space. And that's very, very powerful. Something else to note here is that the consequences in a sequence of patterns generate forces that must be resolved by another pattern. So for example, we saw that we originally applied the strategy pattern to resolve the force of tightly coupled solutions that were hard to evolve. And that resolved that particular force, but it created a new consequence. Namely, you ended up with the potential for a configuration nightmare of too many strategies that weren't working together in semantically coherent ways. So to solve that, we applied in the sequence the abstract factory pattern. And that pattern helped us to be able to group together semantically compatible strategies, thereby making sure that what we put together would work for the particular domain or context in which it was being applied. And that was great, but it had a consequence as well. And that consequence was you could end up with a bloat of too many factories and too many strategies. So we applied the component configurator pattern to be able to address that particular consequence as part of its context. And what it yielded was a design that was able to be expanded and contracted much more readily and even dynamically as the particular domain context or runtime environment dictated. So these are patterns that you'll see occur together very frequently. In fact, when we talk in later parts of the course on examples having nothing whatsoever to do with Corba or Corba-like middleware, you'll see that these pattern sequences still apply. They're still valuable. Just to underscore the point, we've been using Corba and avionics control systems to motivate a lot of what we've been talking about. But don't think for a minute that the patterns we're discussing are in any way, shape, or form limited to these applications and these domains. We'll see that a lot more as we go further on in the course.